Hey guys, welcome to day 6. Today we're looking at two things, the intermediate value theorem, and we're going to look at some limits with absolute values. So let's start with the intermediate value theorem. This is a theorem that I believe that you will understand, you'll come to understand very well. Articulating it is much more difficult than understanding the concept. So I'm just going to start talking about the concept, and we'll come up with the definition in a little bit. So here's what we have for intermediate value theorem. By the way, the AP test is totally fine with you referring to it as the IVT, but it's good to, the name, when you say the full thing, intermediate value theorem, does kind of help us understand the concept behind it. So here's what we have. First off, the intermediate value theorem only works for continuous functions. So for the IVT, our function f of x here must be continuous. And again, we know from previous videos, a continuous function is a function that doesn't have any jumps or holes or vertical asymptotes, so it's connected. Okay, so with a connected function, it's the only time we can use the IVT. If you use the IVT to prove something true, and you don't know if the function is continuous or not, it's not going to be a valid reason. You must have continuity to use this. So here's the idea. I'm going to start by sketching a graph. And what I'm going to do here, I have a point at A and a point at B there. I'll call the x value A for the left point. Its y value I'm going to call f of A. The second point has an x value of B with a corresponding y value of f of B. Okay. And here's what I know. F of x must be continuous. I'm going to add to this on the closed interval AB. Okay? So we're on the closed interval AB. So I'm just going to connect these points, making sure that my function is continuous in between. So I might do something like this. There we have it. So by looking at this graph, we can tell that the graph is continuous. I don't see any holes. I don't see any jumps, any vertical asymptotes. So what the IVT guarantees is that if a function is continuous on a closed interval, in this case AB, wherever, AB could be like 0, 10 or 5, 11 or -2, 2, it's saying that we will hit somewhere between A and B, an x value between A and B, we will hit any y value that's between f of A and f of B. Okay. So if you think of, like, let's say f of A was 2. Right, if this was 2 over here and this was 10, there has to be somewhere between A and B, some point, let's call it C. There has to be a C somewhere between A and B where f of C equals 5, or f of C equals 9, or f of C equals 3. I have to hit every number between my y values of 2 and 10. Okay, but let's go back to our letters here. So if I choose any y value between f of A and f of B, like let's say right here, there has to be somewhere in here there must be the point C comma f of C. Somewhere in there, we have to hit that. Okay? Again, we're using letters to kind of generalize here. Sometimes students get a clearer picture when we start putting numbers in. Okay. Now, why do you think f of x has to be continuous for this to be true? Okay, I want you to think about that. Why does f have to be continuous? Well, let me resketch my f of x in a non-continuous graph, right, in a discontinuous graph, and show you why it has to be. So let me just kind of erase this graph a little bit. Okay. So now let me put in a graph that's discontinuous and show you what happens. Did I hit that y value f of c anywhere in there? Well, I didn't because I jumped over it. So f of x there is not continuous anymore. So I don't have to hit every value between f of a and f of b. Okay. Now there's another question. What about numbers less than f of a? Like y values less than f of a or greater than f of b? Well, I could still hit those, but it's not guaranteed. I am guaranteed to hit every y value between f of a and f of b. Okay. So I'm going to draw back this. I'm going to go back here to our regular continuous function here. Let's just undo. There we go. Okay. So here's how the calculus book defines the intermediate value theorem. Again, this definition, I am literally holding the math book right now because I struggle personally with remembering exactly how this thing is stated. However, I understand the IVT very well. Okay, so here's what it says. If f of x is continuous on the closed interval AB, f takes on every value between f of a and f of b for at least one value c on that interval, closed interval AB. Blah. Hideous, right? Let me show you just a quick example of what I mean using numbers. Okay, here's what we have. Let's say that f of 1 is so here's what we have. F of 1 equals 8, and f of 7 equals 20. Okay, that's what we know. We also know f is a continuous function. Okay, so the question is there a value c on the interval, sorry, it should be closed, on the interval 1, 7, where f of c equals 11? So what do you think? Here's what we know about f. We know f of 1 is 8, right? When x is 1, y is 8. F of 7 is 20. When x is 7, y is 20. And we know that f is continuous. Is there a value c somewhere between 1 and 7 where f of c equals 11? Well, again, my question is this y value intermediate, right, in between this y value and this y value, right? Can I go from 8 to 20, right? Can I have a graph that's continuous, that's connected, go from 8 to 20 without hitting 11? No, it's impossible as long as f is continuous. So the answer is yes, due to the IVT. But when we justify things, we need to be careful with our justifications. Here's what I'm looking for. The answer is yes, since f of 1 equals 8, and f of 7 equals 20, and f is continuous, there must be a c on 1, 7, where f of c equals 11 due to the IVT. Okay, so when you justify on this, I want you to state the surrounding values. You'll need to do that. You need to state, even though the prompt stated this, you need to state that f is continuous. And then you must justify this due to the IVT. That's the kind of process we're going to have to take. State the surrounding values, state that the function is continuous, and then we call it invoke the IVT. Okay, we'll see more of these. These often come up in the form of tables, so we'll see that in class tomorrow. Okay, last thing, let's talk about limits with absolute values. Go ahead and just copy this question into your notes. So here's our problem. We have the limit as x goes to 3 of absolute value x minus 3 over x minus 3. So one of our strategies, the first thing we do is we plug in our x value and see what happens. Well, it's pretty obvious here. When I plug in 3, I get 3 minus 3, which is 0. The absolute value of 0 is 0. So I get a 0 on top, and I get a 0 on the bottom. Now, generally, this means whole, right? And I said it's always going to mean whole, but we got to be careful if we have absolute values, okay? Absolute values are a place where 0 over 0 might not necessarily mean a whole. So let's think about this a little bit. Eventually, we'll take a look at the graph here, too. But I want you to think about, right, when we have absolute values, I want you to really think about left-hand and right-hand limits. So let's think about limit as x goes to 3 plus. Of this function. Now I want you to think about limit as x goes to 3 minus of the same function. So let's start with a number to the right of 3. Okay, we'll choose an easy one to calculate at first. So a good number that's just to the right of 3 is 4. What happens when I plug in 4? So if I plug in 4, I'll switch colors just so if I plug in 4, I get 4 minus 3 over 4 minus 3. Well, on top I get 1. The absolute value of 1 is 1. And on bottom I get 1. So this is going to 1. Let's try it with a number a little bit closer to 3. like, but still on the right side, 3.5. Okay, I get 0.5 on top. Absolute value of 0.5 is 0.5. Then I get 0.5 on the bottom. And again, I'm getting 1 coming out. Let's try a number even closer, like 3.1. Well, 3.1 minus 3 is 0.1. Absolute value of 0.1 is 0.1 over 0.1. Hopefully you're seeing that no matter how close I get to 3 from the right side, my function is always at 1. So we can, just through kind of trial and error here, we can figure out that the limit as x goes to 3 plus of this thing you can tell that that's going to have to be 1. Okay? Well, let's think about the limit as x goes to 3 minus. And this is where things get really interesting. Okay? So what I want you to do is choose a number to the left of 3. Let's try 2. So here's what I get. I get 2 minus 3, absolute value over 2 minus 3. Well, on top, 2 minus 3 is negative 1. Here's the change. The absolute value of negative 1 is positive. I'm getting a positive 1 on top, and 2 minus 3, I get a negative 1 on the bottom. 1 divided by negative 1 is negative 1. Well, let's try a number even closer to 3. Like, we'll skip 2.5. Let's go straight to 2.9. 2.9 minus 3, absolute value over 2.9 minus 3. Again, on top, I get negative 0.1, but the absolute value makes that positive 0.1, but it stays negative 0.1 in the denominator. Which again gives me a value of negative 1. So what I'm getting here is my left-hand limit. My left-hand limit here is equaling negative 1. So here's what I get. A left-hand limit of negative 1, a right-hand limit of positive 1. What does that tell me? Let's put it all together. What does that tell me about the limit as x goes to 3? Right, no plus or minus this time. What does that tell me about this function? Well, it tells me that the limit does not exist because the left and right-hand limits are different. Now, think about, so the limit doesn't exist, so our function is going to be discontinuous. What type of discontinuity would this be if we have a right-hand limit of 1 and a left-hand limit of negative 1? Well, that tells me that this is going to be a jump discontinuity. Okay, I'll show you guys, we're running out of time, I'll show you guys the graph on that in class tomorrow. All right, talk to you guys later. Bye.